actually uses the same hardware as the original one. There's no difference in hardware. I'm gonna show it in the demo. So what happens when you install BluePill inside a system which was already BluePilled? So this is a question about nested virtualization. As Dino said today, if we didn't handle this nested virtualization correctly, then it would allow for very easy detection by just trying to create a test virtual machine. And if it fails, then something is wrong. Of course, the easy way for cheating is just to intercept CPU ID, just like Dino said, and just pretend to the operating system that this processor doesn't implement SVM. But again, this is very easily detectable by a user who is aware that actually she bought SVM capable processor. So we need to handle nested VMs. So here we have hypervisor. So this is BluePill, right? So BluePill called VMRun to actually run the operating system, the native operating system, which was BluePilled. So this is our operating system. This is BluePill hypervisor. So let's say that this BluePill operating system now tries to create virtual machine by itself. So it calls VMRun. And of course, so first it creates VMCB, let's say call it VMCB number 2, because this was VMCB number 1. So it first creates VMCB number 2, but instead of creating virtual machine, we are going back to hypervisor, because hypervisor intercepts any VMRun calls. VMRun is another example of events which can be intercepted. We can intercept any VMRun calls. So we are going back to our hypervisor. And now we realize that this was VMRun called from our guest. So we call VMRun on behalf of this guest by using VMCB2 prepared by this guest. We can actually access this, and we create virtual machine for this guest, which runs. So it's running until some event occurs. The event which this guest said that it would like to intercept. So let's say, I don't know, some interrupt or whatever. So of course we are going back to our hypervisor, not to this hypervisor, but we are realizing that it was intercept from VM number 2. So we resume our operating system just after this instruction. So the operating system thinks that this happened just here, right? That's only a time difference. So the operating system thinks that actually it is a hypervisor, but in fact it's not. Another detection is, of course, by timing analysis. For example, we can assume that this is not a lipstick, it's just a moisturizer. Because people then say, why do you use lipstick during your talks? It's just moisturizer. So we can assume that some instructions will always be intercepted. One example of such instruction is read MSR. Just because to enable SVM mode, we need to set this bit number 12 to 1. So if we didn't intercept read MSR for the EFER register, then it would be trivial for the guest to notice that this bit is set to 1, which is suspicious, right? So we always can assume that read MSR is intercepted. So not surprisingly, the time needed to execute read MSR inside VM takes more time than on a native operating system. So, well, that sounds obvious, but the first problem for the detector is that detector should have some baseline to compare with. So we need to know how much time read MSR, how much time it's necessary for read MSR to execute on a native operating system, and how much time it's needed to execute inside VM. Like we've seen on the Dino's presentation that it took like 200 cycles for the native operating system and 3000 on a inside virtual machine. But if you wanted, but we knew that first it was not virtual machine, and then we knew that it was virtual machine. So we had some baseline to compare with. If we consider that there are many different processor models, it's not so obvious that by just seeing some result like 500, we don't know. Maybe it's optimized processor, and this 500 is maybe inside VM, or maybe it's a slower version of some processor, and 500 is just a normal latency for this instruction. But even if it was constant, even if we had this baseline, even if we could look into the optimization guide, which has a table of the latencies of the instructions, and even if it worked, then there's an easy way for us to cheat about cycles. It's easy for us to cheat about the time for the guest. So again, here we have hypervisor. It calls vmrun, so we're executing inside virtual machine. And let's say we call read MSR here. So this is intercepted. We go into hypervisor. Hypervisor does do something to service this call, and then it restores the execution of guest. So it took like tx extra time, extra cycles. So we can use, there's a special field called TSC offset inside VMCB in this control block, which says, which is the offset which should be added to guest timestamp counter before it's resumed. So we just add minus -x here. So if guest called read TSC instruction, which is used for reading timestamp counter, and read another and remember the result, and then it called it again here, so it will not notice this extra time, right? Just because we subtract this time which we added. So the only reliable way for getting time on a machine is to use external timer. And one of the examples of external timers is NTP, Network Time Protocol. But again, Network Time Protocol can be, like, the packets can be intercepted by hypervisor. So we need to use either some kind of like VPN over SSL or some NTP over SSL or VPN, or we need to use some custom NTP-like protocol, which I don't think is very practical. And also we have another problem with this, because when we used read TSC for time profiling, it returns the number of cycles, while when we are using NTP, it only returns the number of milliseconds. I don't know the accuracy of NTP, but it's around milliseconds. So this is not very good, and we cannot use it for actually adjusting our clock, because our clock can be cheated. So we need to rely only on packets we get. So I don't believe, and I stress the word believe because I might be wrong, that this might be used for effective detection. But we'll probably work on this, so maybe you should expect a talk how to detect blue pill within the next few months. Okay, this is what I said. So blue pill is just a way for silently moving the running operating system into virtual machine, hijacking operating system and inserting our own thin hypervisor. It can be exploited in many various ways, not necessarily malicious, but malicious are one of them, of course. And one example, very simple example. I didn't have time to develop anything more complicated. This is a network backdoor, something very similar to DeepDoor, which I presented in January, but this time implemented with the help of this blue pill technology. So we use two debug registers to hijack execution of those two functions, receive net buffer list and send net buffer list from NDIS. And blue pill intercepts debug exception. So once those functions are going to be executed, debug exception is raised, it's serviced by BluePill, and the execution is returned to guest, but guest doesn't even realize that the debug exception was raised because hypervisor can decide if it should pass the exception to the guest or not, or just service it by itself. So we are servicing the debug exception by ourselves, so guests don't even realize that debug exception was raised. And of course, BluePill takes care about protecting those two debug registers, so that if the guest tries to write to those debug registers and then reads, they will behave like if they were not used, right? So they are emulated for the guest. So not even a single byte is modified inside NDIS data structures, nor NDIS code, nor any code or data of kernel. So there's completely, so like here we have BluePill code, and here we have kernel, data, code, and there's no modifications introduced by this code. This code is just standalone, sitting somewhere here. So like we seen Alex's presentation just an hour ago, and he was talking about, oh, this method is very stealthy because it requires only one double word modification inside the system. This method requires zero double word modifications. And of course, delusion, as every good network backdoor, comes with own private TCP/IP stack, which is based on lightweight IP, which is a popular stack used for microcontrollers. And now this is how the demo looks. This is the scenario, right? So we have a computer which will be BluePilled, and we have a attacker computer which will connect to this delusion backdoor. And delusion is created in such a way that it observes incoming traffic to all TCP or UDP ports, and once the magic packet is sent to one of the ports, whatever, open or closed, it's not important. So if the packet is magic, then delusion hijacks this packet and serves the packet and send reply. And also another computer should be used for debugging BluePill over serial connection. And in this demo, this computer and this computer will be one computer. So you will see a serial console for debugging and command prompt and netcat for sending those packets to delusion backdoor. Okay, demo. So I really wanted to show you a live demo because it's cool to see how you can actually play 3D chess on Vista when it's BluePilled, because it still can use all your 3D graphics card features, but I couldn't show it on this demo because the program which I use for capturing were able to capture only 1 frame per second, which is not very good. So we have Vista Beta 2, which is not compromised yet. We see the hardware. We have Western Digital, NVIDIA, Lighton. We have Realtek for network card, AMD Athlon, something. You see that I first run kernel strike to get access to disable kernel snatch checking, and now I just loaded delusion, right? So the system got BluePilled. And this is the output from the delusion. I'll just